When you stack every service, database, and routing into a single server, you create a rigid monolith that fractures under heavy traffic. The traditional XAMPP environment perfectly demonstrates this limitation. It bundles Apache, MySQL, and PHP into one tightly coupled execution space. Cloning this server to handle more users duplicates the stateful database processes. Multiple isolated databases trying to write to the same shared files leads straight to data collisions and system crashes. To build resilient systems, local development environments have to mirror production-grade orchestration. That requires decoupling the edge routing from the application logic and isolating the database state entirely. This repository solves the monolithic bottleneck using Docker Compose to orchestrate a multi-node, load-balanced cluster. This schematic reveals the macro-level topology, the client browser, the Nginx edge proxy, and a cluster of 3 XAMPP nodes. Look closer. Only the first node acts as the primary, carrying the database capabilities. The other 2 are strictly stateless web replicas. To truly understand how this orchestration routes traffic, we need to trace a single secure web request from the browser all the way down to a specific database query. Visualizing this request lifecycle bridges the gap between abstract configuration code and the physical network routing that keeps the system online. The trace starts here. An incoming HTTP request from the client arrives at the Nginx edge proxy on port 80. Nginx immediately issues a 301 redirect, rejecting the unsecured connection and forcing the request to upgrade to port 443. The packet returns encrypted. This is SSL termination in action. The Nginx container decrypts the incoming traffic at the edge, meaning the backend Apache servers never spend CPU cycles processing encryption overhead. Setting up local encryption usually relies on self-signed certificates. Browsers flag these as security risks, throwing up warning screens and blocking API requests. This architecture bypasses the issue using a tool called mkcert. It installs a local certificate authority directly into the host operating system's trust store, creating valid certificates that browsers accept without warnings. Centralizing this SSL management at the edge proxy keeps the backend application configurations pristine and environment agnostic. With the request decrypted, it moves into the upstream routing block inside Nginx. It now faces a routing choice between the 3 available XAMPP backend nodes. The nginx.conf file dictates this choice, using a specific load balancing algorithm, least_con. The default load balancing method is round robin, which hands out traffic in an even sequence, 1, 2, 3, regardless of how backed up a server might be. Web requests have variable processing times, and a complex database query might tie up a server for seconds. Least Connect continually monitors active connections and routes new traffic away from busy servers to prevent bottlenecking. Our decrypted request is sent straight to the specific backend node currently handling the fewest active connections. This connection-aware routing guarantees maximum resource utilization across the entire cluster, keeping traffic flowing without manual intervention. The traffic now enters the XAMPP Web internal Docker Bridge network. The external boundary stops at Nginx. Everything inside this network is hidden from the host machine. To enforce this isolation, the Docker Compose file uses the expose directive rather than ports for the XAMPP containers, keeping the 8080 range traffic strictly contained within the internal bridge. The packet crosses that internal network boundary and successfully reaches XAMPP2 on its designated port, 8081.
The Apache httpd vhosts.conf file is listening, ready to intercept the incoming traffic. The virtual host directive reads that 8081 port number and maps the request directly to the correct physical document root directory, like /www/site1. Aggressive network isolation protects the application layer. No client can bypass the Nginx proxy. All traffic must pass through the edge's security protocols first. Now that the request has hit the document root, the PHP application needs to initiate a PDO connection to fetch the data required to render the page. Here we hit the critical architectural constraint. If all 3 XAMPP containers attempted to run their own MySQL daemons against the same shared storage volume, the system would immediately corrupt the data and crash. The configuration solves this by suppressing a database service entirely on nodes 2 and 3, intentionally turning them into stateless web servers. When a stateless node needs data, it reaches across the internal network to query port 3306 on the primary node.
Inside, the XAMPP data volume maps the database files directly to the host machine, ensuring data persists even when the container's lifecycle ends. Strictly decoupling ephemeral application execution from persistent data storage is the mandatory prerequisite for horizontal scaling. We can prove that this complex structure works by validating the internal routing through automated command line testing. Running a fast curl loop against the load balancer verifies the distribution. The responses rotate evenly across all 3 available containers, proving least con is actively routing the traffic. Testing database persistence confirms that when the Docker cluster is intentionally shut down and restarted, the MySQL data remains completely intact on the host volume. This empirical testing confirms that the configuration effectively eliminates the bottlenecks of a legacy monolithic stack. The final system functions as a unified, high-performance cluster. Traffic distributes fluidly from the edge proxy, balances evenly across the stateless web nodes, and safely queries an isolated database. Achieving this requires the precise orchestration of Docker Compose, an Nginx reverse proxy, mkcert for local SSL, and Apache virtual hosts. Manual server configuration is fragile and difficult to replicate. By defining these relationships as code, the architecture becomes perfectly reproducible. Building local development environments that rigorously mirror production topologies is the ultimate defense against deployment failures.